Your test is next class. Quiz today. Mark your own. Here we go. Hey, this is a parallel plate question. As soon as I see a parallel plate question, Julie, as soon as I see a parallel plate question, probably I'm not using any equation with an R in it. Probably. What is the magnitude and direction of the electric field between the two plates? So electric field, I can calculate as KQ over R squared. I just said I'm probably not going to be using an equation with an R in it. The other way to find electric field on your formula sheet is the voltage divided by the distance, how far apart the plates are. It looks like the voltage that we travel through here is not 500. I think it's 750 because we're starting at negative 250 and ending up at positive 500. The distance is 0.055 meters. So that's going to give me the magnitude of the electric field. How big is that? Let's find out. You get 13,600, is that right? So 13,600. If you said newtons per coulomb, I would give you full marks. Here, because I used volts and meters, I would use the other units for electric field, volts per meter. That gets you some marks. Direction. Well, we imagine which way a positive would want to move if it could. I think away from the positive towards the negative. So down or south or something along those lines. I would give you half mark for that, half mark for that, half mark for the magnitude, and a half mark for the direction. Suppose we put an electron at location A, and then we let it go. What will its final speed be when it hits location B? This is the same as picking an object up and dropping it. We can use conservation of energy, G. The only issue here is sometimes stuff falls up, but you know, it's the whole like repel, unlike attract thing. So I'm going to start out by saying, well, KE initial plus PE initial equals KE final plus PE final. I got to be honest, Part B to me for your test would be a little too easy for a written question. I would either have it coming in with a speed, give you an initial kinetic energy, or something along those lines. Or I'd ask you to do something with the speed once you found the speed. Figure out how much time it would take to go across or something like that, or what the acceleration was or something like that. Here, it implies we're starting at rest. And when I get to the top, I've used up all of my energy. Kinetic energy hasn't changed since Physics 11. It's still a half mv squared. Potential energy, what kind of energy this time? This time it's electric potential energy, and I'm going to use QV. I'm not going to use the one with the R in it because that needs 2 points and also means point charges, and I don't have 2 point charges. That's a messy F right there. So I guess the speed is going to be 2 times Q times V divided by M square rooted. It's going to be the square root of 2 times Q. They didn't tell me. It's an electron. 1.6 times 10 to the negative 19. Technically negative, but I know I'm taking the square root and I want a positive answer, so meh. Voltage, 750 volts is what we're traveling through. Divided by mass, they didn't tell me. It's an electron, 9.11 times 10 to the negative 31 volts. Volts, kilograms. And then square root of that. Do you get 1.62 times 10 to the 1, 2, 3, 4, 5, 6, 7? V equals 1.62 times 10 to the 7th meters per second. If you got that, 4 out of 4. Otherwise, I would probably go something like this. Half mark for that, 1 mark for that, half mark for that, No, you know what? I give you a full mark for that because that's the key equation. Half mark for the numbers, half mark for the answers. Does that add to 1, 2, 3? No, you know what? Let's give you 1 whole mark for the answer. 1, 2, 3, 4. No, something like that. Oh yeah, this is much more realistic. Number 2, this is much more of the level of difficulty you could expect to see as a plate question. Now it wants the final speed, but we have an initial speed. So this is the same question as we just did, but you can imagine, Rebecca, we're throwing something down, so it's got some initial kinetic energy. But the fact that they said speed, this is a job for conservation of energy, G. KE initial plus PE initial equals KE final plus PE final. My final potential energy is going to be 0 because that's right there. Because that right there is ground level. It's going to be a half mv initial squared plus q voltage equals a half mv final squared. I mean, I guess I could get the v final by itself. I'd multiply everything by 2, divide by m and square root. You guys do it that way, or did you all get an answer and then change it? You did it that way? Okay, so for Connor, we'll go like this. Times by 2, times by 2, times by 2. Hey, those cancel and those cancel. Divide by m, and then square root. I think you end up with v final being the square root of mv initial squared plus 2qv divided by the mass. Is that what you got, Connor? Yep. So it's going to be the square root of, am I moving an electron or a proton? Electron. Mass 9.11 times 10 to the negative 31. V initial 2.1 times 10 to the 5th squared plus 1.6 times 10 to the negative 19. V, 150 volts, divided by 9.11 times 10 to the negative 31. Guess I got to put the top in brackets. 9.11 times 10 to the negative 31 times 2.1 times 10 to the 5th squared plus 2 times 1.6 times 10 to the negative 19 times 150, close bracket, divided by 9.11 times 10 to the negative 31. Check for typos. mv squared plus 2qv all divided by, and then we square root. You get 7.26 times 10 to the 6th. So if you got that, 7 out of 7. Otherwise, how would I give up part marks? Good question. I'd probably give you 1 mark if I saw that, 1 mark if I saw that. Oh, I got to get 7 marks out of here, Mr. Dewick. How? 1 mark for that. That's 3, 4, 5, 6, 7. I don't know. I'd come up with a better marking scheme than that, trust me. So that was some plate questions. Can you give yourself a score out of 13? So we've been looking at static electricity, electricity that isn't allowed to go anywhere. The only way we let it travel somewhere was if we had a strong enough electric field that it was able to ionize and jump the gap as a spark. Now we're going to say, all right, suppose we put it into a circuit. You look at some of this in Science 9, although I think in Science 9 it isn't done terribly well in terms of how it's taught. So, circuitry. I always enjoyed teaching this one. I enjoy solving circuit puzzles. I find them almost addictive as little puzzles to solve. If you keep up with the homework in this, you're going to be great. Generally, kids find this unit pretty good. Voltage, first of all. Lesson 1 is Ohm's law, which you learn about in Science 9, but I don't think terribly well. Fill in the following key facts about voltage. This next bit is actually on your test next class. What was the definition of voltage? How did we define it? It was energy per Coulomb. In fact, a volt was defined as a joule per Coulomb. That was 1 volt. If you wanted an equation, we said voltage was equal to the potential energy that a little test charge, and that divided by the magnitude of a little test charge at that location, that told you how many joules of energy every Coulomb of charge had. What were the other words for voltage? Or electric potential. Again, Drake, not to be confused with electric potential energy. So, what happens inside a voltage source, inside a battery? We're going to be looking almost entirely at direct current during this unit. Everything that I teach you, Sam, if any of you go on into electronics or engineering, also works for applied current. The problem with alternating current. The problem with alternating current is you have the current going this way, then this way, then this way, then this way. Hey, Math 12 students, what kind of a graph do you think you handle with that? It's a trig function, and I can't assume you've seen it before. But everything that I'm showing you works fine for alternating current. What happens inside a voltage source? Well, in a voltage source, work is done separating charges. Work is done separating charges. And what I mean by that is normally these negatives and these positives would flow together. So what we do is we have some kind of chemical reaction, typically inside a chemical battery, where we put negative charges here, we have positive charges there. That's a bit of a fib, James. Technically, all you're really doing is moving electrons, moving negatives, but moving an electron to the left, mathematically, Drake, that's the same as moving a proton to the right, even though the protons don't actually move. We do work in separating charges, and then we put a boundary or a buffer between them so that they can't come back together during the battery, but they do want to come back together because it all comes down to, Drake, like charges and unlike charges. Here it's unlike charges attracting. They want to get back to each other. We give them an alternate path. The circuit symbol for a voltage source looks like that, where the short line is the negative side and the long vertical line is the positive side. This would be a single cell. If you have more than one cell combined, that's actually technically what we mean by a battery. A battery actually is several cells lined up. I'm going to be lazy and sloppy. Most of us will just call this a battery, even though we recognize it's a single cell. Sometimes you'll hear me call it a cell, but I'm sloppy that way. And here's our analogy that we're going to use for solving circuits. This is a trick I stole from another teacher, not my idea, but it's great. To help us understand what's happening in electric circuits, again, it's helpful, Kayla, to have a real-life mechanical analogy. And the analogy that we're going to use, we're going to pretend that every single circuit is a ski hill. In any ski hill, you start at the top, you end up at the bottom. Otherwise, you haven't skied the hill. recall in the previous chapter, we said that voltage is sort of like height. Sort of. So the voltage at a point in the circuit is how high you are on the mountain. If you're at the highest voltage, you're at the top of the mountain. What if you're at the bottom of the mountain? What's your height? Robbie, what's your voltage? You've used it all up. Okay? The voltage gain from the battery, we're going to treat this like a chairlift. In fact, you're often going to hear me call the battery a chairlift. All a chairlift does is it gives you extra potential energy, gravitational potential energy, by raising your height. All a battery does is it gives the charges extra electric energy by raising their voltage. Then the resistor, that's the ski hill. This is where you ski down. So if you want to, on this ski hill analogy, you can put a battery like that, and then the symbol for a resistor is wavy lines, and you get back to the bottom. In any ski run, Sam, the chairlift lifts you up, the battery gives you more energy, and then you ski down to the bottom. You go through the resistor, losing your energy. Now let's talk a little bit about current flowing charges. What happens if I connect a wire to one side of a voltage source? Well, there are a whole bunch of negatives right here. I guess they'll repel each other, so they'll go whooshing along here. You'll get a couple of extra negatives, but not too many, because there's nowhere for them to travel. There's nowhere for them to travel. But if so, almost no charge moves, and then you can cross out the word almost. We're going to say, for all intents and purposes, nothing happens. I think a few electrons would go shooting into that wire trying to get away from each other, but really nothing. What if the wire forms a continuous loop? Well, now you're going to have a whole bunch of electrons going along the wire to get to the positive end. So the first thing we're going to say to you is, for a circuit to occur, you need a closed loop. A ski run's not a ski run if it doesn't lead anywhere. No one's going to go on it. Hi, here's a ski run. You're going to end up in the woods miles from everybody and not on the bottom of the mountain, and it's not going anywhere. It's not going to be a popular trail. There is a problem with this, though. Okay? I said that voltage is energy per coulomb. The problem with circuit B is there is nowhere for the energy to go. Well, the energy's got to go somewhere. That circuit B, the energy is going to go up into heating up the wires. This is a bad circuit. In fact, we call this here a short circuit. The wires will get hot. Now, this isn't always a bad thing. Your stove elements are basically a controlled short circuit. That's why they get so hot. So it's not always bad, but this would not be good. These wires would get warm and warmer. They might even melt the insulation. They might even get red hot, depending on how big the battery was. So why is this a better circuit? The energy is used up in the light bulb, and it goes into turning on the light as opposed to heating up the wires. The energy's got to go somewhere. Well, let's make it useful. Turn the page. So, electrons need a completed circuit for current to flow. Put your pencils down, look up. So we just saw a video and you heard them talking, Julie, about current. What the heck is current? We're going to define it. Current is how fast charge flows in a circuit. It's the rate of flow of charge. Anytime I talk about the rate, anybody remember? What am I dividing by? So it's going to be the amount of charge divided by time. This is your first equation on your formula sheet, although we'll almost never use it. We're going to use this to derive other stuff, but once in a while. And current then, I guess as units, would be coulombs per second, but we give that a name, we call it an amp. 1 amp means that 1 coulomb every second is flowing by. Oh, also recall that any charge Q is a certain number of fundamental charges. So if you know the charge in coulombs, you actually know how many electrons or how many protons are in that charge. You just divide it by 1.6 times 10 to the negative 19 to find out how many there are. So you can actually relate a current to the number of electrons that have moved through a circuit, as an example. A 1.5 volt AA battery cell is rated at 0.750 amp hours. Say, what? When connected to the motor in a portable CD player, once upon a time, we used to listen to music on these things called CDs. They, at the time, seemed revolutionary. They held a whole bunch of songs. And you would put them into this device, and the device would spin the CD, and a laser would read the music from there. It was wondrous. But now we've moved on beyond that. Anyways, suppose you had a portable CD player, and you know that the cell provides 0.25 amps of current. First question, how much charge, how many coulombs is stored in the cell? Well, I know that current is coulombs per second. How would you get the Q by itself? Yeah, you get Q is it. Current is measured in what units? Amps. Time, I'd like in seconds, but actually, you know what? Right here, that is a current time measurement. If any of you get into electronics, you're going to find often we'll talk about batteries in terms of how many amp hours they have. What you're really saying is how much charge is stored in that. And the amp hour is a useful unit of measurement because if a battery has, for example, 3 amp hours, what it's telling you is you can run a 3 amp device for 1 hour. You can run a 1.5 amp device for 2 hours. You can run a 6 amp device for half an hour. That's all you got. So it's a quick way to do some nice, easy arithmetic if you're wanting to know how long will my battery last. So I have as a measurement 0.750 amp hours, but coulombs is not measured in amp hours. Coulombs is measured in amp seconds. So I need to convert this hours to seconds. How? Well, I want hours to cancel. I want seconds on the top. Who remembers how many seconds there are in 1 hour? 3,600. So, how many coulombs of charge is there in this AA battery? 2,700 coulombs of charge. You can't get it all out at once. That would be tremendous. Because 1 coulomb, I've already told you, if you absorb that all at once, that's a massive amount of charge. How many electrons are stored in the cell? Well, I know that charge is the number of electrons, I'll use a capital N, times the elementary charge. So if I want to find the number of electrons, that's going to be the charge in coulombs divided by the elementary charge. It's going to be 2,700 divided by 1.6 times 10 to the negative 19. And I get 1.69 times 10 to the 22 electrons. C says, how long will the cell power the motor? I could get this T by itself because I know Q and I know I, 0.250. Why don't I do that? So let's see. T is going to be the current divided by the charge. What current is this device drawing? Is that right? No. Did I do that? No. Charge divided by current, Mr. Dewick. Thank you. Charge divided by current. Thank you. How many coulombs of charge are stored in this battery? We said 2,700. Divided by how many amps does this particular device need? 0.25. What do you get? This is going to give you an answer in seconds, yes? 10,800 seconds. Let's convert that to hours. So it's going to be 3,600 seconds is 1 hour, and I think you'll get 3. Double check me. Now, really, the easy way to get this, and this is why amp hours, we're not going to use them in physics, but they're used all the time in electronics. Really, the easy way to get this, well, if it's 0.75 amp hours, I'm using 1/3 the current, I'll get 3 times the length, 3 hours. That's why that's such a nice measurement to use. So, let's continue our ski hill analogy. I said voltage was like the height. What's current like? Current is like the flow of skiers up and down the mountain. Higher current, more skiers. Lower current, fewer skiers. Since electrons flow at a constant speed in a circuit, we're going to assume that the skiers all use their skis to control their speed, so they're all going at the same speed, which isn't realistic, but the analogy breaks down, but it still works. Okay? Here's our problem, though. One problem that we encounter with this analogy is that in a circuit, it is the electrons that flow from a lower voltage to a higher voltage, but we would like to mathematically say current flows downhill, not uphill. We would like to say things go from higher, a bigger voltage, to a lower voltage. It's much more intuitive. Our brains work better that way. So, first of all, we're going to focus on the positive charges, the nuclei. The uphill flow of electrons is mathematically the equivalent to the downhill flow of positive charges. An electron moving to the left, Sam, is the same as a proton moving to the right. Even though I know the protons don't move, I'm going to pretend they do. So, what we call current is the downhill flow of positive charges. In fact, some books will call this conventional current. And if we're ever asked about electron flow, electrons will flow from negative to positive. So example 4 says, draw the direction of electron flow. I'll do that in red. Electrons would flow that way, which is yucky. Current, I'll do in blue, is defined as from the positive. So here's the current, Here's the current. Oh, I think I forgot to say the letter I is used for current. So I is for current. Current flows up the chairlift and then downhill. It goes up the chairlift and then downhill, as opposed to the other way around. Okay? You can use the remainder of class to